In this lesson, we will continue the discussion of rotational motion by learning about the concept of rotational kinetic energy. Okay. Once again, we'll start with our table comparing translational motion to rotational motion. I always like to start with this because we usually have a little bit less intuition when it comes to rotational motion than translational motion. After all, we certainly spend a lot more of our time going from here to there than we do spinning around in circles. And some of you may feel like you spend a lot of time spinning around in circles, figuratively, I suppose, but literally, we don't spend a lot of time rotating. So it's helpful, I think, to always focus on the analogy between rotational motion and translational motion. So we've learned so far about the rotational motion variables. We've learned kinematic equations to go with them. And in the most recent lesson, we learned about Newton's laws. Sum of the forces is mass times acceleration. Sum of the torques is equal to moment of inertia times angular acceleration. Well, if you remember in our study of translational motion, what we studied next after forces was kinetic energy. And we learned that objects have energy of motion, which we call kinetic energy, and the expression for that was 1/2 mv squared. That quantity turned out to be useful because in cases where mechanical energy is conserved, it turns out to be a pretty simple way to solve certain kinds of problems. Like a box sliding down a ramp, for example, is very easy to solve the problem using conservation of energy. Well, it turns out there's rotational kinetic energy as well. And at this point, you might even be able to guess what the equation for it is. 1/2 m. Well, the rotational analog of mass is moment of inertia, so we'll put that there. And then we have v squared for translation. Well, the rotational analog of speed is angular speed, so we've got omega squared. Okay, and what this tells us is that objects that are rotating have kinetic energy just like objects that are going from here to there. If you rotate one twice as fast, in other words, if you double omega, then you will increase its rotational kinetic energy by a factor of 4. You could also, if you rotate something that has a bigger moment of inertia, then it will have more kinetic energy. Now, this quantity, rotational kinetic energy, is useful for the exact same reason that translational kinetic energy was useful. In many circumstances, it's the easiest way to solve a problem. Let me give you an example. Okay, let's say that we have some kind of incline or hill, and we're going to have a circular cylinder up at the top of that hill, and it's a solid cylinder. And I'm going to start that cylinder up at the top of this hill at rest. And let's say, furthermore, that the height of this hill is 1 meter. Okay. We're starting it at rest. So V0 is equal to 0. Then I'm going to allow this cylinder to roll down the hill. And the question is, what speed will the cylinder have at the bottom of the hill? Now we could attempt to use Newton's laws to solve this problem. We have to know what the torques were on it, the forces, and it is possible to solve the problem that way, but it's quite complicated. A much easier way to solve the problem is to use conservation of energy. Okay, what we'll do is we'll recognize the fact that the energy of this cylinder at the top must equal the energy of the cylinder at the bottom. So we'll solve this just like we solved conservation of energy problems of translational motion, except we have another term now. We have a term that includes rotational energy. So we'll have at the top that ball has potential energy, gravitational potential energy, which is given by mgh1, the initial height, plus its original kinetic energy, 1/2 v1. I guess I called the speed at the top v0, so let's call h at the top h0. That makes more sense. Squared, plus its rotational kinetic energy at the beginning, 1/2 I omega squared. That'd be omega 0. That must equal its potential energy at the bottom, plus its kinetic energy at the bottom, plus its rotational kinetic energy at the bottom. Now, this time, since we said that it's not moving when it starts out at the top, this term will be 0 because z0 is 0. And if it's not moving, it's not rolling either. So that will also be 0. Excuse me. If we define h equals 0 at the bottom, then at the bottom of the hill, h1 will be equal to 0, so it won't have any potential energy at the bottom. So at the top, we have only potential energy. That potential energy would be equal to m times 9.8 meters per second squared times h0, which in my example is 1 meter. At the bottom, we have 1/2 m v1 squared plus 1/2 I. What is I for a cylinder? So at this point, you need to look it up in the table, either in a textbook or on the internet, moment of inertia for a solid cylinder. And you will find that it is equal to the mass of the cylinder times the radius of the cylinder squared. So I will replace I in this equation with mr squared. Okay, so the I here becomes mr squared here. Then we still have omega 1 squared. Well, if you notice, we now have a mass in every term on both sides of the equation. So let's divide both sides by the mass, and then the mass cancels. That's good, because I didn't tell you the mass. We don't know the mass. Now, it appears that we're stuck, temporarily at least, because let's see, the left side of my equation is good. I don't have any unknowns over there. But on the right side of my equation, I don't know the speed. I don't know the radius of the cylinder, because I didn't tell you. And I don't know the angular speed either. So it appears that we have 3 unknowns and only 1 equation. But we're not stuck, because there's a relationship between the speed and the angular speed. think about that for a moment, okay? If this cylinder is rolling down the hill, then it would not be possible for the cylinder to be turning slowly. In other words, going around like this slowly, but moving down the hill quickly. That's not going to happen. Okay, it's also true that I can't have it the other way. I can't have this thing spinning like crazy really fast, but barely creeping down the hill. That's not going to happen either. If it's rolling down the hill quickly, then both its rolling speed, its angular speed, and its translational speed both have to be high. In other words, z and omega are not independent of one another. They are linked. We learned earlier when we first started learning about rotational motion that the link between the speed and the angular speed was z equals omega r. So I can solve that equation for omega. Omega is equal to z over r. And let's plug this in down here for omega. All right, I'm going to go ahead and multiply the 9.1 times the 1. So that gives us 9.8 meters squared per second squared equals 1/2 v1 squared plus 1/2 r squared. Now, omega squared is v squared over r squared, based on what we did up there at the top. Okay, now look what happened. I have r squared, and I have r squared in the denominator. Those r's cancel. That's good, because I didn't know what, I didn't tell you what r was. So we now have 9.8 meters squared per second squared equals 1/2 v1 squared plus 1/2 v1 squared. Well, 1/2 v1 squared plus another 1/2 v1 squared is just 1 v1 squared. So 9.8 meters squared per second squared equals v1 squared. Take the square root of both sides, and you get that v1 is the square root of 9.8, which I will do on my calculator, and I get 3.13. 3.13 meters per second. Now we're done. So the key is you approach this problem just like you would approach any conservation of energy problem. The only difference is that if something is rolling, you have an extra term in there. You have the rotational kinetic energy term in addition to the potential energy term and the 1/2 mv squared term. So let me give you a couple of those check your understanding questions. Okay. Let's say we have at the top of the hill if we have at the top of the hill we have a large ball and a small ball both start from rest at the top of the hill. So there's one, and then we have an identical hill, and there's a big ball at the top. Okay, they both start from rest. On identical hills. Okay. And then the question is which has the greatest speed at the bottom. I recommend you pause and think about it for a moment. And then when you're ready to hear the answer, I will tell you. Okay, are you ready? Well, they have the same shape, and since they have the same shape, their moment of inertia is going to have the same M and R dependence on it. So in the last problem, the example I just worked, remember the mass and the radius both canceled out. So we're not going to have any difference between the balls, even if they have a bigger mass, one has a bigger mass or a bigger radius. So they will both have the same speed when they get to the bottom. A hoop. Now, which one is going to be going the fastest when they get to the bottom? Now, you may actually need to look up the moment of inertia here. So stop, look up the moment of inertia of those things on the internet or in your textbook. Think about what you think the correct answer is. When you're ready, I will tell you. Okay, are you ready? Well, we need to know the moment of inertia of the two objects in order to answer this question. The moment of inertia of the hoop is mr squared. The moment of inertia of a ball is 2/5 mr squared. Since the ball has a smaller moment of inertia